Hello physics students. Today we're going to be talking about what happens to light when it travels through different materials. Now just a reminder that light is a transverse wave. That means that the vibrating electric and magnetic fields oscillate perpendicular to the direction that the electric and magnetic fields oscillate. So for example, if light is traveling this way, the electric fields are oscillating like this, up and down, and the magnetic fields side to side as the light is going this way. So again, the oscillation is perpendicular to the motion of the wave. Also, light obviously travels through a vacuum. The sun is across outer space, and basically the sunlight comes to us even though there are no atoms there. Sound cannot travel through vacuum, but light can. But light can also travel through certain materials, not all. For example, this reference table is sending out green light toward the camera, toward your eye. I can put this plastic calculator cover and it blocks the green light. It cannot go through the plastic, obviously. But if I put a piece of glass here, right, piece of glass, the reference table, the green light from the reference table does go through the glass. Obviously, you know light goes through glass, but it also goes through, for example, water. So you see here, when I put the reference table behind, you see green light also, red light also passes through. So it doesn't matter the color. It goes through glass, through water, also through oil, right? So you can see this red light through this vegetable oil as I put it, the reference table behind. So not all materials, but it does go through certain materials. What we're going to be talking about today is what happens to three things regarding that light wave. What happens to the speed of the wave when it goes through a material that it could pass through? What happens to the frequency of the wave when it passes? And what happens to the wavelength of the wave when it passes through a material. So to show you that and talk more about it, I'm going to show you another example of light passing through material. Just let me reconfigure the camera. What I have here is a chamber full of smoke and a plastic block. The smoke is only so that we can see the laser light pass through the air. So one possibility is we can allow the light to only pass through the air and reach the screen on the other side, the right side of the screen. Or if I bring this down, then the laser light will pass through the air, then the plastic block, then the air again, and hit the screen on the other side. I could also do that with blue light, which doesn't show up as well in the smoke, but really shows up nice in the plastic block. Or green light, which is a nice happy medium. It shows up pretty well in the smoke, in the air, and then nicely in the plastic block. So the light really races across this chamber very fast. Like for example, if I say ready, set, go, and turn the light on, we could see that the light strikes the paper on the other side pretty much instantaneously. Ready, set, go. And you see, in fact, the time that it would take to race across this smoke chamber is about a billionth of a second, maybe even less than a billionth of a second. Too small of a time to perceive. Now, when I send the light through the air and then the plastic block and then the screen, it actually takes a little bit longer because light travels slower in the plastic than it does in the air. So again, you can't perceive the difference between the two motions because it looks pretty much instantaneous on our perception. But nonetheless, it is true that light slows down in this plastic block. And the question is, why does that happen? So let me now show you another demonstration. Hopefully I can make you understand why it is that light slows down in this plastic block. Now once again, light is vibrating electric and magnetic fields. And when that light passes through a vacuum, there is nothing to affect the vibrations of electric and magnetic field because a vacuum literally is empty space. There's nothing there, no atoms in a vacuum. But when light passes through a material, there are atoms which are made of protons and electrons. And then what happens is that electric field, because the electrons have charge to them, will create a force on the electrons. Furthermore, if the electric field is oscillating, the force will oscillate. So the electrons experience an oscillating force on them because of the light passing through them. And with an oscillating force, there will be an oscillating acceleration. However, the electrons have mass, which tends to resist the acceleration. And so a very interesting thing happens when we have an oscillating force on a mass. What we're going to see is that there is a delay in the response of the oscillations. So I have here the demonstration that I used in the simple harmonic motion unit, the mass on a spring. Remember, I showed you resonance. I can oscillate my hand at this end, and we'll see the car respond with an oscillation. But this time, let's look a little bit closer at the rhythms and look really closely to see if we could see a delay in the response of this compared to my hand. So I'm going to start oscillating, and the car will oscillate. Now, the first thing that you could note is that my hand and the car are oscillating at the same frequency. So if my hand's moving at 1 hertz, the car is also moving at 1 hertz, the same rhythm of vibration. However, notice that when the car is still moving to the right, I start moving my hand to the left. And when the car is still moving to the left, I start moving my hand to the right. In other words, the car is a little bit behind in the oscillations. So the oscillations got a little bit too big. Let me dampen them out a little bit, but watch again. So I move forward, and then the car doesn't respond for a while. Move backwards, the car doesn't respond for a while. So when there's an oscillating force on a mass, the mass is a little bit behind because of its inertia. This is why the light travels slower through atoms than it does through vacuum. Because that oscillating electric and magnetic field, then the electron causes the oscillations to sort of be a little bit, we say, out of phase, a little bit behind the original oscillations. In other words, it takes them a little bit longer to catch up to what would have been the vibration electric field without the electron present there. And when something takes a little bit longer, we know from all the way back earlier in the year that its speed is slower. If it takes you longer to go somewhere, you're going slower. So that's kind of the reason why this light travels slower in materials with atoms. Now, the full picture is much more complicated to truly understand exactly how the atoms are affecting the electric and magnetic fields. You need some pretty heavy calculus, differential equations, stuff that's not in this course, obviously. But this nice little demonstration at least gives us that concept of a delay in the vibration, in other words, the phase of oscillation, to help us get a conceptual feel why light travels slower when it goes through atoms compared to a vacuum. So let's begin with the notes for today. Optics 3, this is the third video of this topic. We're going to be talking about the speed of light and something called the index of refraction. So this is just summarizing what we just saw with that plastic block. But let's assume instead of air around the plastic block, we've got a vacuum. We've got a light ray coming in here, and the electric field, for example, vibrates up and down, and the light wave moves to the right, and that's why we call it a transverse wave, perpendicular oscillations to the wave motion. That wave travels at 3 times 10 to the 8th through a vacuum, very fast, as I mentioned during the waves unit. And as I also mentioned during the wave unit, this is such an important number to physics. A lot of theories are centered around the speed of light, and so it's a very fundamental value in terms of the universe. So it gets its own symbol. We don't say V equals, we say C equals 3 times 8. Well, you could write V, and that's fine. You're not going to get it wrong. But just so you know that when you see that C, it means the speed of light. When the vibrating electric and magnetic fields encounter atoms, like in glass, water, plastic, whatever, oil, then they obviously cause the electrons, which have charge, to also vibrate, because electric field creates force. A vibrating electric field creates a vibrating force, which creates vibrating motion. That creates, as I mentioned, some delays in what we call the phase beyond the scope of the course, but the electrons oscillate, and that then results in a speed that's less than 3 times 10 to the 8th because of the atoms sort of oscillating with the electric fields and the magnetic fields. But then when the ray emerges from the atoms and returns back to a vacuum, it's not like a car that's going 30 miles an hour and hits a patch of mud and slows down to 20 when it gets out of the mud. The car then will just continue at 20, the slower speed, from 30 to 20, and then it comes out of the mud at 20. No, as soon as it comes out of the atoms, it returns back to the original, what it had before it encountered the atoms. It returns to 3 times 10 to the 8th. So that's the way light behaves as it goes from a vacuum, atoms, vacuum again. So let me create a pause, give you a chance to copy these notes down. All right, now, if I were to ask you, do you think light slows down to the same speed when it goes to water versus when it goes to glass? Different atoms, different materials. You would probably say, no, I don't think so. I think that in glass it will have a different speed than in water, and you would be correct. And the reason why is because there are more atoms or less atoms packed into or different substances. And also, there are different kinds of atoms, different kinds of chemical bonds between those atoms. So the speed will vary for every single material that the light goes into. So there is something called the Index of Refraction that physicists invented to quantify how much light slows down in different materials. That's what we move on to next. Index of Refraction. It is defined by the symbol N, lowercase n. It's the speed of light in a vacuum divided by the speed in the material. 3 times 10 to the 8th times some smaller speed because of the atoms means the index of refraction is greater than 1 for all substances that have atoms in there. So because this is smaller, we get a bigger answer over here. So, and the slower the speed gets, the bigger the index gets. So bigger index, smaller speed, inverse proportionality. Also no units, we got meters second divided by meters per second. Now this formula is on the reference table. I'm going to show you it in a minute where it is. But first, I want to point out, now, if the speed is decreasing in a substance, something on the other side of this basic wave formula has to also change. This got smaller, one or both of these would have to get smaller. And it turns out that it's the wavelength that gets smaller, not the frequency. And the reason why is because if the electric field is oscillating up and down, the electrons are going to oscillate at the same frequency as the electric field. When they're propelled up, they're going to move up. When they're propelled down, they're going to move down. So the frequency doesn't change. What that means that if this stays constant, when this gets smaller, this also has to get smaller. And so there's another formula on the Regents reference table. If you take the ratio of any two indices of refraction of material 2 versus material 1, that ratio is equal to the speed 1 over speed 2, or wavelength 1 over wavelength 2. So we could use this expression if we wanted to find the new wavelength instead of the new speed in the other material. Now, as I said, these formulas are on the reference table. I think maybe green will show it better, so let me show you where they are. So we're on page 5 in the wave section, and you see here that, right here, you see that we've got this n equals c over v, right where my index finger is, and then two formulas down, we've got this n2 over n1 equals v1 over v2 equals lambda 1 over lambda 2. So those are the formulas in the wave section of the reference table. All right, so I'll create a pause, give you a chance to copy these notes down. Let's do an example. So, all right, so here's our example. Light has a certain wavelength. I should have put in a vacuum. Maybe I'll squeeze it in here. So has that wavelength in the vacuum, determine, oh, no, comma, determine the speed and the wavelength in glycerol. So the first thing that we're going to do is calculate the speed in the glycerol. And we could use this basic formula. So the glycerol, and I forgot to mention, the indices of refraction, there's a whole list over here, okay? This is page 2 of the reference table, where the electromagnetic spectrum is of the last unit, and you see at the bottom we've got this table of indices of refraction. And so you see, first of all, air is at the top with an index of approximately 1.0. What that means is that light goes pretty much the same speed in air as it does in a vacuum. And then you see that the biggest index on this whole table is diamond, 2.42. Light goes the slowest in diamond, and that kind of makes sense. We know diamonds are very hard and dense materials, so light goes the slowest there. But in our case, we're using glycerol here. 1.47 is the index that we have to use in our calculation. So again, page 2, we find our indices. 1.47. C is 3 times 10 to the 8th, the front cover of the reference table. I won't come to the camera again. I don't want to make you too dizzy. And speed is unknown. So what I'm going to do is maybe think of this as a fraction here, cross multiply. 1.47 times V equals 3 times 10 to the 8th. Divide both sides by 1.47, which gives us 2.04 times 10 to the 8th. Again, less than 3 times 10 to the 8th. It's slowed down because of the atoms in the way. So go ahead, I'll create a pause, copy these notes in your notebook. All right, next thing, the wavelength in glycerol. Well, you would find this on the reference table, but you look up, and here's your formula that tells you how the wavelength varies based on the indices of refraction. So I'll erase this to make room, but basically this is what we would find in the reference table, as I mentioned. Now there were 3 terms. The speed part I'm going to skip. I'm just going to use the wavelength part. Now the second material, it goes from a vacuum and then it goes into glycerol. So N2 is the glycerol, which we looked up as 1.47. And that means I'm going to put the wavelength of the glycerol here. That's what I'm looking for, the lambda 2. The lambda 1 is what it was in a vacuum. But what about the index 1? What's the index of refraction in a vacuum? Well, if we were to calculate, we would put the speed of light in a vacuum here, and the index of a vacuum is 3 times 10 to the 8th, c, over the speed of light in a vacuum, which is 3 times 10 to the 8th. So whenever you're looking for the index of a vacuum, it's exactly 1. Okay, so we'll just put a 1 down here. Cross multiply, 1.47 times lambda 2. 1 times 5.9, 10 to the minus 7th. Divide both sides by 1.47, and you get about 4.01. So the wavelength shortened, right? As I mentioned, the speed gets smaller, the wavelength gets smaller, the frequency stays the same. Okay, so that's what you have to remember. All right, so let me create a pause so you could copy these notes down. All right, so that's it for today. Again, we learned what happens to light when it goes into other optical materials. The atoms cause a decrease in the speed and a decrease in the wavelength, but the frequency stays the same. Those are the 3 concepts, the 3 things that you have to know about light traveling from one medium to another, or going from a vacuum into some other material. The equations here, reference table, so you need to be able to find them, and the indices of refraction are also in the reference table. You need to be able to find them for the various materials. Okay, I hope you enjoyed the demonstrations. I hope you enjoyed the physics. I'll see you in the next physics video.